Thanks for coming. We might have more people coming later, but we have about an hour for the session, so let's start. My name is Oskar Elek. I'm an incubator fellow at the UCSC Open Source Program Office, and this will be a workshop slash status update on PolyPhy, which is a data scientific and visualization package we've been developing for about a year and a half. Oh, hi.
Hello.
Yeah.
Yeah.
Hi. How are you?
Nice
Welcome.
to meet you.
We just started. Maybe that side is better because we'll be project organizer. So this is going to be a workshop on PolyPhy, which is the sort of upcoming interdisciplinary toolkit for complex network reconstruction. Where I say complex networks, you'll see what I mean by that. I want to give a shout out to a few people. First of all, sort of the key stakeholders of this project. How do I hide this? So Joe Burchett, we started this work together in 2019. For a while, we worked with a prototype called Polyform, and PolyPhy is a sort of descendant of that. I'll talk about it later. There is Angus Forbes. He's a professor at Purdue. He was at UCSC when I came here. His specialty is visualization and computational media. And finally, there's of course Carlos and Stephanie, who are the directors of the Open Source Program Office, and also Cross, which supports this project and provide guidance in all things open source. In this list, Joe is sort of the main PI, the main expert on board when it comes to astrophysics, which is really where scientifically this project has started. There is a great deal more people. Some of these are senior PIs working with us. Some of these are students who contributed to this project. Some of them are UCSC students, some of them are external students, mainly through GSOC. There are artists in these lists. I can't give a shout out to everyone, but this is a contribution of, or sort of collaboration of many people. To summarize this project in sort of one cheeky picture, here is some kind of a futuristic ant. I generated this with AI, so it's not exactly as I wanted it. But basically, what this project is about is allowing us to think about complex structures in nature, but also in society or in culture. So both physical and artificial and conceptual structures, which are just too big to think about in the whole, and using metaphors from nature that actually can help us think about this and also work with these kind of structures. So this project is focusing on networks. I cheekily made this ant here think about the structure of the anthill without ever being able to comprehend the anthill. So this is kind of us human beings trying to understand complex phenomena that are way bigger for any single individual to comprehend, and using models which are not only useful for data scientific purposes, but also are accessible to people's intuition. Because as you probably know, many models that we use today are not accessible to intuition. I.e., we don't know what neural networks do, even though they generate beautiful pictures like this. So the organism that inspired this project is slime mold. You might have seen this thing in the forest somewhere. This is a very ancient organism. It's called a protist, which is in fact its own family. So it's not a fungus or a plant or even an animal. And they developed sort of network intelligence, to put it bluntly, to explore their environment, scour for food, and basically grow what amounts to optimal transport networks. And we use this nature-inspired intelligence to develop a simulated model and a data scientific tool that can generate all kinds of patterns. So you can think of it as a generalization of slime mold. of network patterns that you can fluidly modify and get all of these patterns out of one simulation that resemble different physical processes, and hopefully I'll convince you later also artificial phenomena. Before I start talking about all these conceptual things, I want to show you a quick demo. So this is the most basic version of PolyPhy, the two-dimensional pipeline. And the data that this is showing, and oh my God, it's so slow. Okay. Yeah, so I think Zoom is messing with the performance here, but yeah, this is too slow to even show in real time. This is supposed to run like 200 frames per second, so 5 milliseconds. Yeah, 5 milliseconds a frame. It's currently running at 2.5 frames per second, so it's not very interactive. But even then, you'll probably see that since we started, the sort of the pattern of the data, which is the green points here, the green sort of yellow gradient, is being fitted in real time with the simulation, which is visualized in red, and is creating these patterns all around the data set, but also exactly where the data actually is defined. Let me see if I can do something with this. Yeah, okay, I guess it must be the Google Slides there interfering with this. So anyway, this is a GPU-driven simulation, which means that if something else is using the GPU, you get suboptimal performance. So normally this responds pretty much instantly. I apologize for this lagginess, but you know, what you see is basically an interface. Let me share the screen back here. So yeah, what you see is an interactive interface which runs purely in Python. This is a sort of GPU connected application that opens a window on your local computer, but it can also run in a remote setting if you don't use the graphical interface. The graphical interface is useful just because you can interact with the simulation, you know, once it runs it at its full speed, and you can even edit it. So I'm now placing very slowly a bunch of new points for the simulation, and in 100 iterations or so, it's going to actually adapt to this, but that will take a while in this remote setting. So anyway, especially because the performance is so laggy, I just want to encourage you to open your own instance. So if you go to GitHub/PolyPhyHub, you'll find there is a repository PolyPhy and some like auxiliary tools. So if you just go to the PolyPhy repository, clone it, and then run it the way I'm running it, which is from the experiments Jupyter production, you'll be able to basically run the same thing. The data that I'm using to run this demo are also in the repository. So yeah, while I was talking, the patterns actually adapted to these data points that I just placed interactively. So this is kind of the playground. The two-dimensional tool, is not the main focus of this. The main focus is the three-dimensional pipeline, which I'll be showing you later. GPU resources permitting.
So Oskar, if it's too early for this question, then I'll wait. Can you hear me?
Yeah, I can hear you.
So in general, the inputs to the process are a set of points in space, and the result of the process is some sort of set of connections between those points that are in some sense optimal. Is that right?
That's right. Yeah. So this is just a screenshot of what I was showing you. The simulation takes discrete points, as you said. These are two-dimensional, but they can be 3D, and tries to fit this network in the data. What I didn't show you is that you can actually disable this auto patterning of the algorithm and just fit to the data and nothing else. So I'm just showing you, I was just showing you this because you can kind of see the nature of these patterns that arise from the algorithm itself in these areas where the data are missing. And why this structure is optimal, as you said, Joel, is just because it creates the shortest connections possible to just interconnect the nearby data points, which is what the organism does as well. Does that make sense?
Yes.
Yeah, and this is a good place to probably say, please feel free to ask questions anytime, interrupt me. This is more or less an informal session. So,
and so if you think of connections between points as consuming some kind of resource, do you parameterize this process by some constraints on that resource somehow, or if you let it run forever, will it sort of fill the page with connectivity?
well, the algorithm tends to settle in an equilibrium. What I'm showing you on this slide is basically the equilibrium. If I disable the auto patterning property of the simulation, all of these patterns that surround the data are actually going to disappear. So it's going to be only the data set that actually has any connections found or reconstructed. When it comes to consuming the resource, every data point emits a certain amount of marker. I'm going to explain what the marker is actually in a second. And that marker is diffused into the environment. So it can't really sort of diverge because there is a sort of dynamic equilibrium that's being maintained by the simulation, where you inject a certain amount of this marker at every iteration, but then also remove some of it by what is called an attenuation or dissipation, you might call it. And so
that's modeling the physical process. That's how this line model does it, I guess.
Yeah, all of these things very much mimic the physical processes.
Cool.
Which is Zoom just told me I was signed out. Is that no? That looks it's running, right? Yep. Okay. I don't know what that was about. So yeah, for the people in the room, I'm happy to show you the demo after we stop sharing because it apparently doesn't like the Zoom running. So yeah, but you can also try on your own machines. For those who are actually trying it, if you clone the repository, you can run this thing from the experiments Jupyter production folder by running this command, Python selecting the PolyPhy to the discrete pipeline, and then as a file using the data/CSV/sample to the linear data set. Yeah, I don't know if you can parse that. Actually, I can just paste it in chat. So yeah, there's a folder where you can run this from, and the command to launch the pipeline. You just need the Python environment, and you also need to set up the requirements before. So that would be PolyPhy. So you need to run this to install the requirements or the dependencies, and that's from the root directory. So wherever your repository is, you need to run the install requirements first, and then you can run the actual software. Okay, so yeah, thanks for the question, Joel. I'm going to explain the algorithm in a second, but these are good to have cleared out in the beginning. So I want to tell you in the next 10 or so minutes the story of this project, because I think it's a very curious story, and if you heard it before in one of the previous workshops, for instance, just feel free to browse Twitter for 10 minutes. But this is the cosmic web. So this is kind of the inspiration that started it. For those who don't know what the cosmic web is, it's a large network of gas and plasma and dust that fills the intergalactic space. It's basically a remnant of the Big Bang. And cosmologists are very interested in finding this structure because it basically defines the scaffolding of the whole universe. So just to give you an idea how big this structure is, when you actually zoom into the middle, you see that even this little zooming contains thousands of galaxies. So basically every bright sort of spot in this image centered around this mega cluster in the middle is an individual galaxy. Now, if we had images like this of the real universe, we would be done. We would have the solution to this problem, but this is not an image of the real universe. This is a simulation. So this is the first supercomputer simulation that Springle et al. In 2005 published to demonstrate what was already conjectured for about 3 decades, which is that this structure is very likely there. And what we should be actually looking for, we should be looking for this gigantic network. They call these tubes, or these channels of gas, filaments. Now, since then, many much more sophisticated simulations on supercomputers have been done, and we see this network structure pop up in all the properties of the universe. Here is a slice of the Eagle simulation, which is about a decade later. And these are temperature and metallicity fields, where also you can see this network structure. These are 3D visualizations, so it's a bit messy, but this filamentary structure basically pops up on you everywhere. But yeah, as I was saying, we don't actually have the real cosmic web, and the reason for this is that it's just extremely sparse. It doesn't glow on its own, it doesn't emit any light, it barely scatters any light. All it does is some degree of absorption, which is really mostly how astrophysicists probe this structure. But you can't make an image of it, and you can't actually generate a map of it, which would sort of allow you to do data scientific analysis on this of this object, which is really what we started to do in this project. Here is sort of an indirect imprint of this structure. you can see all this sort of variation. This is the cosmic microwave background radiation field. And all these little spots are caused by the imprint of the filaments onto the cosmic microwave background radiation. So we have plenty of evidence that this thing is out there. We just didn't have a map of it, and that's what we set out to do in this project. Now, in 2019, there was an unexpected inspiration that came from the artificial life community, where this artist, Say Jensen, flooded Twitter with these beautiful animations of virtual slime mold. This is about 1 million agents simulated in real time on a GPU. And this project actually inspired us to use the same approach to try and reconstruct the map of the cosmic web, because this thing clearly grows networks, which very much resemble the ones that the cosmic web has and other network-like phenomena do. You can also adapt this to consume data, so to say, as you'll see later. So as I mentioned, the Physarum polycephalum, or the slime mold, is a very ancient organism. Is a protist that evolved to grow these networks to optimize its body structure and cover as much ground as possible and consume whatever decaying environment it can find in the forest. The way it does it is it follows chemical gradients emitted and diffused from food sources, as well as its own sort of physical body. And as you'll see in a second, the algorithm basically does the same thing, but in a more mathematically sort of optimal way or consistent way. We definitely weren't the first to leverage this computational, this interesting property of the slime mold or its simulation to grow optimal networks. For instance, here is a study from 2010 where Japanese researchers actually grew a very similar network to the Tokyo railway system, just feeding the slime mold, the actual slime mold, not the simulation, sort of the centers of main urban areas of population density map of Tokyo, and the algorithm or the slime mold found, you know, a network that very much resembles the actual Tokyo metropolitan system, the transportation system. Many people actually use the real slime mold to solve computational problems. Most of these are geometric problems like maze solving and Kolmog's Hall computing. And this has been summarized in this really quirky, interesting book by Professor Adamatsky. His current work now is about listening to mushrooms and trying to find out if they actually speak to each other, which I find fascinating. It's basically just signal statistics. But yeah, why this applies to the cosmic web is just, well, there is a quote from a 2018 paper that very nicely summarizes that filaments appear to be highways of the universe, the transport channels along which mass and galaxies get channeled into higher density cluster regions. So basically the slime mold, the cosmic web interconnects all the galaxies into one, what you can think of a transportation network. And that's exactly what slime mold solves by its own behavior. And if you render this cosmic web image a bit yellow, maybe you can see the similarity between these two. And of course, it's not one-to-one. We had to design it to actually work for that particular sort of specific domain. So how does the algorithm actually work? It's actually pretty simple. So we were talking about a massively parallel multi-agent simulation. So you have millions of agents running in parallel and exploring the domain. What this animation shows you is actually just one agent exploring a field of data. So the data are colored orange in here, and the agent is green. The data are basically discrete points, as Joe was asking before. 3D points in 2D or 3D space, points in 2D or 3D space that actually emit sort of this virtual marker that then signalizes the agents where to look for the data. And this marker field is constantly being diffused, which means that it covers more space and actually guides the agents towards it. So yeah, the marker field emitted by the data and also by the agents if the agents emit the marker field, they start generating almost hallucinatory patterns on their own, which we actually saw in the demo earlier. So the green, as I said, the green particles are the agents. They explore this grayscale marker field, and basically they try to stochastically maximize the yield of the marker that they find. Sometimes they can deviate just because sometimes the probabilistic sampling sort of diverges them to lower densities, but they turn back eventually. And so, and yeah, the agents emit what we call a trace, and the trace is just a trajectory of the agents, basically a line in 3D space or 2D space that we record, and then all the agents together, when you add up their traces, actually form the solution to the problem. So this is the whole algorithm in one slide. So what does this look like in practice? On the left, you see 50 agents just crawling around, drawing random squiggly lines. So that doesn't tell us much. But if you have millions of agents, you actually get an approximation of a continuous solution to the network reconstruction. And this is a very novel thing because suddenly you have a scalar field that you can interpret as a map. For instance, in the context of the cosmic web, astrophysicist Farhan is on the call right now. For instance, they interpret this as the actual density field that represents the cosmic web. There is a translation step that has to happen to sort of map the densities of the slime mold or the simulated slime mold to densities of the gas, but that step is already comparably simple to reconstructing this whole network because it's just a value mapping.
Can you say anything about how well this approach matches a continuous simulation based on gravity? I mean, does it actually give you something like the same answer?
I mean, we think of it as, or at least I think of it as like a meta heuristic on top of gravity. So in no place in the simulation there is the gravitational equation
right.
guiding the agents, but the agents have a nonlinear step where they are drawn to pools of the deposit, which effectively is like gravity in the simulation. So we're not simulating gravity because obviously we're trying to solve a sparse reconstruction problem. So we wouldn't even know all the possible sources of matter to correctly compute gravity.
Well, so I guess I'm assuming that there is some best approximation that is your gold standard for what you're trying to match up to, and value is to do it in a much more computationally inexpensive way. And I guess I'm trying to figure out what is that gold standard? How do you know if you got the right answer or not?
That's an excellent question. We've been, breaking our heads on this for a while, and the answer is the actual supercomputer simulations that cosmologists produce. So if you have, like one of these simulations that I was showing earlier, for instance, this one right here, that takes months on a supercomputer to actually calculate.
Sure.
And so, but what it does give you is a complete density field that contains the effects of gravity, the effects of electromagnetism, basically plasma physics, thermodynamics.
Sure.
All of these forces are accounted for that we know of in the universe. And this is the golden standard that you're asking about. So when we are actually running the simulation on real data set, like observed data from the universe, we first calibrate it on these reference data sets. So we treat the rigorous simulations as the golden standard. We calibrate the simulation.
Will you talk today about how well they match up?
I probably have a plot somewhere in the extra slides. I can show it after we're done.
Just curious.
Yeah, it is a pretty decently sort of aligned mapping. It's not completely linear, but we actually solve for the step by doing one additional remapping step, which is calibrated on on these reference data sets. So I won't be talking about that because that's actually a work of somebody else from the team. But what you at least get is sort of a monotonic relationship between the density of the reference and the density of the simulated slime mold. And then any value mapping is just a question of optimized table lookup.
Okay.
But yeah, I mean, the calibration is only accurate insofar as our cosmological simulations are accurate. So these are, of course, always in development, but you know, nevertheless, is the best thing we have. So this is just a quick demo, which is hopefully faster than running it right now, which actually shows fitting to about 1 million halos from one of these canonical simulations. So this is the golden standard that we calibrate to. And you see a real-time fitting of the slime molds to all these millions of data points. This video is sped up twice, I think. So in the video, the fitting took about 20 seconds, maybe 15 seconds. So in real time, it takes under a minute to actually fit a three-dimensional model to millions of points using maybe 10 million agents. And that's on a single GPU. So I can run it on this very laptop that I'm presenting from. This is a sequence from the early prototype, which we call PolyForm. So PolyPhy looks a little different. It has a better user interface. It's still missing some of the more kind of cosmology specific features, but we're working on implementing those, and that's already the relatively easy part. Anyway, so to speed things up a little, so I want to jump through some results that actually sort of define the project. So this was our first result in 2020. We mapped 37,000 galaxies of the Sloan Digital Sky Survey, only very near galaxies, so like close galaxies to our own. On the cosmological scales, 37,000 galaxies is nothing. It's really a tiny neighborhood, but is enough to create sort of a testable map, or you can call it a hypothesis. So we validated this map against independent observations, which were absorption measurements of the cosmic web, absorbing light of distant quasar light sources. And yeah, this kind of went viral in 2020. We published a report with UCSC media office, and it got picked up by all of these major outlets. So that was, of course, very exciting, that people care about this, and it encouraged us to work on this problem further. We ran a study of what people call fast radio bursts. So fast radio bursts are, here's a visualization, basically large sort of bursts of electromagnetic radiation that originate somewhere in the universe, in a random galaxy, and then it reaches much further than the source galaxy, and we can detect it on Earth. They were discovered in 2010, so pretty recent. The reason is that they are so short that we basically need very fast responsive equipment to even detect them. So we ran a study of one such radio burst where the energy from this flash passed through a big chunk of the cosmic web, and using this simulation, we actually reconstructed the cosmic web and shown that the observed absorption or dispersion in this case matches the one that you predict from this cosmic web map. This is a more recent study led by Farhan Hashan, who is actually on the call, I believe. Yeah. And yeah, do you want to say in one sentence or in 3 sentences what this was about, Farhan?
Sure. Yeah, this is sort of mapping out the cosmic web using, in the same way you would do in observations, but this is in the simulations, the illustrious TNG cosmological simulations, and kind of this is showing like evolution of the cosmic web, with going to the right, is earlier times, kind of how it evolves with respect to galaxies. And this is sort of the precursor to applying this method or applying the PolyPhy stuff, the slime mold stuff to this method so that we can actually get a much more detailed map of the cosmic web.
Yeah, okay, thanks, Ryan. So these were kind of, this was a cross-section of different scientific results we got in the area of cosmology and astrophysics. Here is one that actually comes from digital humanities. So this was an attempt to map out abstract spaces that come from deep learning sort of networks or deep learning models produced when you parse large language corpuses. So this here is a visualization of the word-to-vec embedding for the Wikipedia 2017, the English Wikipedia 2017 snapshot. And what it gives you is basically a map of about 300,000 tokens, where every token represents a word or a phrase, sort of detected and extracted from Wikipedia. And you can actually run not just visualization, but also queries on this data, where starting from a source word, you can get related words to that and basically create sort of an understanding of what's in this corpus, which is normally pretty difficult to grasp. They live in several hundred dimensional spaces. And so we try to provide insights into these spaces. The project also created different artworks. So for instance, this was a visualization that we done with Issei Mori, who's at UC San Diego right now. And this was just a quirky way of showing, what would the cosmic web look like if it actually was a slime mold. This is more just a fun project, but we've done different sort of art performances, even live performances with music, where the simulation reacts to live generated music, and I'll show you one later. There is time. So anyway, so this was about the algorithm. This is just an overview of the main properties of it. There is a scientific contribution, which is actually Monte Carlo sampling of the agent behavior, which is compared to a deterministic sampling that was kind of limiting what you can do with this before. So that's that made it much more applicable to this data scientific analysis. It usually runs pretty fast, unless you're sharing your screen on Zoom. So under 1 minute, you get continuous reconstructions of 2D and 3D data set on a single GPU. It's good if the GPU is some like higher tier, but it runs on lower end GPUs as well. And it's interactive, so you can actually play with it. You can tune the algorithm to the data that you actually loaded, and so it gives you much more sort of close loop to working with the simulation than you would normally have in sort of standard scientific analysis packages. So just to give you an idea of the current status, so PolyPhy has been in development for about 1.5 years. Yeah, this is what it normally looks like. It's implemented in Python entirely, including the GPU code. We use a package called Taichi, which is a cutting-edge technology that just basically compiles Python code into a GPU code, so that you don't have to mess with things like CUDA or compute shaders, which is what we were using before. So this is not limited to any platform or any operating system. It runs on different hardware. So that just goes in the direction of making this as accessible to different users. As I said, this was initially designed for astrophysics, but because these networks are pretty common patterns in nature, but also in sort of cultural artifacts like the linguistic embeddings, we want to make this available to the broader data scientific community. I was already talking about all of this. One of the new results is actually an open source data set, which we submitted. So this was documented in a big summary paper in 2022, which was the 17th data release of the Sloan Digital Sky Survey, which is our source data set in first place. And we attached this open source catalog to it. So everyone in the astrophysics community can actually grab this data and test whatever they want to test on them. That actually includes Farhan's study that he was talking about earlier. Here's the.
Good morning.
Yeah, that's it. Yeah, that's fine. So I was already showing the repository. So I just wanted to talk about some of the sort of community aspects of the project. So the repository and all the infrastructure work was greatly, like the major contribution was from Prashan, who was a GSOC student this summer, and we're still working together on the infrastructure part of the project. So he tremendously helped with the refactoring, which is still ongoing, so that the project is actually much more modular, as I'll show you later. I want to give a shout out to Asfari, who was also a GSOC student, but last year in 2022, who actually built this beautiful website for the project, polyphy.io. So check that out if you're at the computer. I want to give a shout out to Drew Early, who's actually right here in the room. He's the 3D printing master. He also brought a whole collection of models generated, like 3D models generated by the virtual model and 3D printed. And yeah, this is Drew's work, both his master thesis and demos at ACM Symposium on Computational Application. He's actually going to present an update of this in about a week in New York. So yeah, the pictures are of the bicycle helmet, which we actually generated, sort of an attempt to get around the limitations of traditional helmets and then generate something that's much more robust and sturdy. It's not styrofoam. So here's a sample of the pattern. It can actually be printed into a viscoelastic material. This here is work by Austin, who just joined us. Nice timing. So yeah, this is a work on incorporating path tracing, which is the state-of-the-art sort of 3D visualization method for volumetric data. So the earlier prototype had this, but PolyPhy did not. So Austin actually got support of the Core Scholarship to do this work, and we're still working on transferring that to the newest version of PolyPhy. But we have a working notebook which Austin used to generate these images of the Sloan Digital data, Sloan Digital Sky Survey data. Finally, a shout out to Kiran Deol, who is a student of this year's Google Summer of Code. She's from University of Alberta. She worked and still works on a tool to visualize these high-dimensional embedding data after being projected to a three-dimensional space, where you can basically localize and search for a data point. So for instance, if you have tokens extracted from linguistic data, you can search for individual words. Here is searching for football. And then you can actually interactively explore the surroundings of that point and find out, well, what is actually in the embedding space surrounding that point? What is sort of the semantically relevant context of that token or of that word? And this can be also something else than words. So for instance, we are working with a UK startup called Autonomy that actually curate data sets from legal proceedings and also proceedings of United Nations. So they have tens of thousands of documents, handcrafted, like hand curated and embedded in a space, which we then visualize using the tool that that Kiran wrote in JavaScript. So this is an interactive tool that runs in your browser. I think you were
just playing with it
before.
Drain my battery.
Yeah. 3D rendering the browser is not cheap, but yeah. So this is a tool that supports sort of orientation in this data, but also annotations. So on the right, you see a cluster that basically using a brushing technique we marked as semantically related to this word, and that's something that the user can use to sort of segment and understand the space better using whatever sort of conceptualization of the space they want. So yeah, I wanted to talk about the community of this project. There was a slide before, I don't know why I put it here, but basically the community is centered around two artifacts: PolyPhy, which is the software, which I've already showed you, but I still have one more demo coming. This evolved from an earlier prototype called Polyform, which was written in C++, and it wasn't very portable. That's why we decided to develop the Python one in the first place. And then there is a second artifact called MCPM, which is the actual simulation methodology. This stands for Monte Carlo Physarum Machine, which is just a technical name for what this simulation does. And then we have several communities or several sort of segments of communities which are overlapping. We have actual researchers, including myself, working on both of these artifacts. Local students, for instance, Drew and Austin, who are sitting in the room and working with the team on both of these. And then different communities connected to the software itself. I mentioned already several stakeholders and researchers who are external to UCSC. They're contributors, for instance, Google Summer of Code students, and actual users that partially include researchers, but also we're obviously looking to expand the community of users. And finally, artists, to produce these 3D prints and visualizations. Excuse me for a second. So yeah, this is just a quick overview of who is involved in the project. Here is more tabular mapping, but I don't think we have time to go through that. Some sort of pertinent questions to this: how do new members get involved and onboarded? This is something that very much depends. Some of new members of the community come from UCSC, much like Austin and Drew in the room here, and also maybe Yao. And some of them find the project through Google Summer of Code. So several of the contributors that actually created really big sort of chunks of work, they came through Google Summer of Code. There is also external users that just find the project and become interested and then connect to us by, I don't know, searching on Google. I really never know. There is a crew of filmmakers that are coming in December to make a film about this, so they somehow found it. So really, what we need right now is basically just to expand the search, sort of spread the net, and involve more people to create a bigger community. This is a question from the post training. What is the shared purpose or commonalities among members? Obviously, interest in these patterns and networks is one, but beside that, the community is actually very diverse. As I said, some of these are students, some of these are expert researchers who want a particular domain, specific problem to solve or to be solved. Some of these are artists who just like the visuals. I was contacted by a sculptor from Prague who wanted to make sculptures with this. So Drew is actually helping with that, and I think he has one model that is a small version of the sculpture that she's working on. So she actually wants to use heat gun to sculpt plastic based on this. So yeah, we definitely couldn't have come up with that one. What activities do we want to see as a result of participation? Really just creating opportunity, like solving data scientific problems, obviously, but also creating opportunities to for people to get training and mentoring. So for instance, Google Summer of Code is an excellent example of that. We have students who just come and get an experience working on a project that has all these different interdisciplinary facets. I've been sort of trying to map some of them in this, pretty quick, hectic, quick talk, but I see an advantage in actually working on a project that involves so many different communities of researchers and artists, because you never run into danger of just sort of blindly following one particular thread of work. There's always different constraints and requirements that you have to fit into, but on the other hand, also inspirations that come from these communities, and you basically end up building bridges between the communities using the model as like a conceptual connective tissue. Finally, question: how do the activities contribute to growing the ecosystem? Again, in multiple ways. The obvious one is contributions of code or different assets to the repository, creation of websites, basically concrete products, but also creating broader context. So for instance, I try to quickly tell the story of this project. That story is a shared story of dozens of people who contributed, and the fact that it can be told this way, is a result of all of this work, and it creates, meaningful connections to things. So people are not just working on a piece of software that does one thing; they actually grow an ecosystem of ideas and sort of scientific storytelling and visualization. So all of these things are connected and they reinforce each other. There's a question that comes up with open source projects: what's the distribution and balance of power? So we have, I'm the lead developer of the project. I manage all the engineering aspects of it, some of the conceptual work as well, but we have domain experts that actually meaningfully steer the project. So, if Joe Burchett comes and says, well, this should do that, I better implement that rather than just making it my own way. So there are checks and balances. Obviously, the open source program office is responsible for the administrative and management side of the project. So there is no single entity that is actually holding all the power over this software and the community connected to it. I want to show you one quick slide on the design. So this is kind of the main progress since last year. So if you came to last year's workshop, you actually already saw the interactive demo, and that was purely just implemented as a collection of Jupyter notebooks. So that wasn't scalable at all. Throughout the year, we had new contributions. For instance, the visualization work from Austin and the 3D printing pipeline by Drew that still need to be incorporated, but the basic pipelines are now implemented as their separate modules. So basically, PolyPhy is sort of a collection of abstract classes that you can inherit from and then implement a specific incarnation of a given data scientific pipeline. So what I showed you, the demo in the beginning, is what we call 2D discrete pipeline. So really the simplest incarnation of the simulation, where you just feed it a collection of discrete points and then reconstruct networks on top of them, and that's pretty much it. But there is also a continuous pipeline, which I was demonstrating last year, which actually you can use to reconstruct road networks. So we had a very high fidelity reconstruction of the US highways and freeways. Check out the last year's workshop if you're interested to see that live. And of course, the main bread and butter is the 3D discrete pipeline, which then also has several incarnations. So for instance, there's the discrete geometric pipeline that we use for the 3D printing, working with models and meshes. and also a hybrid pipeline where we have both discrete and continuous data. Come in? No. Where we have both discrete and continuous data working together. So you can basically inherit and extend these classes and come up with entirely new pipelines that we don't even really envision. You can also include this code pretty much seamlessly in Jupyter and Colab notebooks. As I said, Colab notebooks won't let you run the interactive window, but you can run the software in a sort of batch mode and generate results in the background. And there is also a growing set of external downstream tools. So, for instance, the tool developed by Kiran that I mentioned, we call this the polyglot tool. This is an external tool that builds on PolyPhy and the analysis that it does, and actually creates these visualizations and sort of computes the distances between these tokens in the embedded space. So, and the reason why this is the case is just we want domain scientists to come up with their own ideas, with their own pipelines, and work with really data that they understand, because we, as a team, obviously can't cover all of that. Okay, so quick demo of the 3D pipeline. You know what? Actually, let me first cover the rest. Hi.
Hi. We reserved the room 12 to 1.
12. Oh.
Yeah.
We just had an hour. Okay.
Yeah, I'm sorry.
Okay. Let me wrap up in 5 minutes. Is that okay?
Okay.
Just really quickly. Okay. So we won't have time for the demo. So really, I just wanted to mention the future of the package. The future is both in terms of research. We want to continue developing new pipelines for high-dimensional point sets. This is to actually enable proper analysis of these abstract embedding spaces, and then do corresponding science with it. In terms of community, I want to mention that we actually proposed an NSF project called POLS, or Pathways to Open Source. That's literally 2 weeks ago. We submitted that. And if this project goes through, we'll have a year of funding to develop sort of professional and community activities around the project. So it's not the grounds to support the software and the science, but actually to support the community of people, of students that can then develop new scientific and applied use cases, as well as people from the industry. And obviously, all the community building activities are being planned. So engaging with local students, but also the distributed context of collaborators across the United States and even globally, not only from universities, but also through Google Summer of Code. So yeah, stay tuned for that. That will be sort of a major kind of critical transition from being locally funded to being actually funded by a federal grant. So hopefully the NSF will find this interesting. I had a few takeaways. I think since we need to clear the room, yeah, I'll skip these. These slides will be linked from the workshop page, so please go back to them and check them out. Kind of the ground point of the project is that using open source software actually enables us to connect all these different contexts, so not just scientific work in one specific domain, but also multiple domains, as well as art that then represents these results, creates kind of an outreach for them. So yeah, without going open source for this project, this wouldn't be possible because, well, that should be pretty obvious why. So discussion at lunch. This is my closing slide. That over there is the actual is a capture of the music performance, like the audiovisual performance with this. So this here is reacting to some beats in the music And most importantly, please take a picture of these or a screenshot. There are links to the repository and the web. If you'd like to support the project, which I would very much appreciate in the name of the whole team, the best way to just connect to what we're doing is follow the Google group, the email group. The link is right here, groups.com/g/PolyPhy news. And go to the repository.
Okay.
And, yeah.
Sorry. We have only 1 hour for our lunch meeting, so we need to.
Yeah.
Sorry.
Okay. Thanks, everyone.